Hello, I am Isa Mashrafi Mahi from AI Beauty department. Today I am presenting the design and simulation of a 5 GHz microstrip rectangular patch antenna using COMSOL Multiphysics. This design serves as a single radiating unit cell element for a C-Band Synthetic Aperture Radar edged array system. Here you can see the project topic of mine, Synthetic Aperture Radar for Earth observation. Now I am directly jumping onto the COMSOL software. This is the window of COMSOL Multiphysics. Now I am click onto the model wizard, then click 3D and then select electromagnetic waves frequency domain, then click add, then click onto the study and then select again frequency domain. At last, click onto the done and the setup is done. Now I have to start the process of the simulation. Here you can see the global definitions, and under the global definitions now I have to add parameters 1. Previously I am listed it and save it to my PC. Now I am direct import it from my PC. Here you can see all the parameters. Now I am click onto the geometry one and then click block, and that is called substrate, and the width is A and depth is B and height will be EAs plus HS. And the XY plane is 0 and the Z plane is EAs plus HS divided by 2. And the position is center and the layer thickness is PAs. Now I click onto the build selected. I am turning off the grid and then again click onto the geometry 1 and add a work plane, and the Z coordinate is EAs plus HS. Now I am click onto the build selected. Again I am click onto the plane geometry and add a rectangle that is called patch, and the width of this patch is L and height is W, and the position XW is minus A divided by 2 plus LF minus Y naught, and the YW is minus B divided by 2 plus W divided by 2. Now I am click onto the build selected. Again the plane geometry, add another rectangle that is called matching, and the width of this matching is Y naught and height is 2 into P1 plus WF, and the position of this matching is minus A divided by 2 plus LF minus Y naught, and the YW position is minus 2 into P1 plus WF divided by 2. Then click onto the build selected. Now under the plane geometry area, I am select the Boolean on partition and then click onto the difference. Firstly, I am click onto here and then add. Now I am click onto the build selected. Again, I am click onto the plane geometry panel and add another rectangle that is called feed, and the weight of this feed is LF and height is WF, and the position is minus A divided by 2, and YW is minus WF divided by 2. Now I am click onto the build selected. Again under the plane geometry, I am click onto the Boolean and partition, then click union. Now I am firstly click here and then here, and then select build selected. Now under the geometry 1, I am click onto the extrude, and the distances is TA. Now I am click onto the build selected. Again, the click onto the geometry 1 and add another work plane, and the plane type is YZ, and X coordinate is minus A divided by 2. Now I am click onto the build selected. Now click onto the plane geometry and add another rectangle that is called port, and the width is WF and height is HS plus 2 into TH, and the XW position is minus WF divided by 2, and YW is 0. Now I am click onto the build selected. Now under the geometry 1, I am click onto the sphere, and the name is far field, and the position and the radius of this far field is B plus PML, and the layer thicknesses is PML. Now I am click onto the build selected. Here you can see the far field is already created. Now I am click onto the definition, and add a perfectly matched layer, and the type is spherical, Now I am select all the part of this spherical. After done this process, now I am click onto the material section, and I am adding the materials, firstly air and then copper. Under the air section, all the things are selected by default. So I am click onto the copper section. The copper section is inside the spherical. So I am remove the upper surface and find out the copper. Now I am click onto the hair and then here, and the copper section is perfectly selected. Again, I am click onto the materials and then click blank material and click onto the upper surface, and the relative permittivity value is ER into 1 minus 1I into 10D, and the second one value is 1 and third one is 0. After that, I am click onto the electromagnetic waves and frequency domain, then add a far field domain. Here you can see all the section of this part is selected by default. Now I am click onto the electromagnetic waves and frequency domain section again, and then add a lumped port. Now I am selected the lump port very carefully. And the type of lump port is user defined, and the ACE is 2 into PH plus HH, and the weight of the lump port is WF, and the direction between lump port terminals is 001, and the Z coordinate would be 1. Here all the things are successfully done. Now I am click onto the mesh 1, and sequence type changed from physics control to user control. Now click onto the size and I am changing it to custom to predefined, and it is normal to coarse. Now size 1, and I am doing the same thing here. Here I am doing the same thing. Now I am click onto the build mesh, and the process of the build mesh is ongoing. Now it is built successfully. You can see. Now I am click onto the study 1. Under the study 1, here you can see the step 1 frequency domain. Now I am click here, and I am customizing. Start from F minimum, stop F maximum, and due to my RAM shortage in the PC, so I am select the step size 0.2 gigahertz. Now I am click onto the replace button. I am successfully done all the things. Now the final part is complete the simulation. Now I will click onto the compute button. Here you can see the process is started. You can see the process is started and the progress is done 6%. And it takes a little bit longer time, so I am pause the OBS studio and wait until the simulation is finished. After wait a little bit longer, you can see the simulation is successfully done. Here you can see S11 return loss plot. We can see a sharp resonant dip precisely at 5 GHz reaching below -10 dB threshold. This confirms excellent impedance matching at the feed point with minimal power reflection. Now I am click onto the 2D far field. Looking at this section, 2D polar radiation pattern across 4 to 6 GHz, we can observe that the maximum radiation intensity is clearly produced at the 5 GHz resonance frequency. Now I am going to show you the 3D far field gain EMW. Moving to the 3D far field radiation pattern evaluated at 5 GHz, the antenna achieves a peak realized gain of plus positive 6.18 dBi and directivity of 7.28 dB. This confirms a strong broadside directional radiation suitable for satellite Earth observation. Now I am going to show you the electric field. Finally, the logarithmic electric field distribution shows a strong energy concentration along the patch edge and field line with smooth absorption toward the outer perfectly matched layer. At last, all simulation parameters meet the electromagnetic requirement at 5 GHz for C-band synthetic aperture radar applications. Thank you.